Rafi is a civil engineering student. We just finished his third year, and he's working on this project to understand how roofs fail in tornadoes. So we have in the wind tunnel now we have a neighborhood of typical suburban houses. This is pretty similar to Angus, Ontario, where in June 2014 there was a tornado that damaged about 100 houses and about a dozen of them lost their roofs. So we're trying to understand the wind speeds and the performance of houses that under failure. So this is kind of a fun project. The houses are modeled to fail. We use actually fridge magnets to hold the roofs down, and it's all properly and scientifically scaled so we can understand.
So maybe today we'll recap where we are so far in the class, and that includes talking about maybe what you're looking at for week 9. I know that some of you haven't looked all the way through that, but week 9 was not just the midterms but also dimensional analysis, which is kind of a misnomer because it's actually dimensionless analysis. And there are some formal ways to do that, but it's really a technique that allows you to do the minimum number of experiments you can get away with and still get some results to be able to say how systems work. And so typically its usage is in for structures in wind tunnels, and those structures might be planes. They might be bridges, they might be skyscrapers with other skyscrapers around them to see what the wind effects are, not in terms of catastrophic damage, but actually in terms of whether a building that you're going to spend half your life in, working life in, has a horrible motion in it that makes people sick. And so they're used to look at those kinds of things. This is a very famous lab. It's Alan Davenport was a guy who worked on, now dead, in Western Ontario, University of Western Ontario, Western so-called, in London, Ontario. Had a boundary layer tunnel lab to look at not so much planes, but really civil structures. And these are doing some experiments. I don't know if those of you who live in Pennsylvania know that we're at the kind of top end of Tornado Alley. He's mentioning here a tornado visited a town in Ontario in 2014. Certainly in Pennsylvania and Ohio in May of 1985, there were tornado outbreaks in western Pennsylvania and eastern Ohio that killed 40-odd people. And also the same day in Toronto, where I was living at the time, just outside Toronto, 40 people died in Ontario as well. So it's very unusual in these areas, but they happen. And actually, I remember there was a twister that touched down in Bowlesburg, where we live, and twisted a sign, a very small one, but they've been known here. And so this is looking at effects of tornadoes on houses. He said that these are scaled houses to represent a subdivision. They've got the roofs held on with fridge magnets to be realistic for when the roof would blow off and break. And it looks at the proximity of other structures around it to see what the influence of those structures are. So it's difficult to be able to get the exact form of the flow patterns when you have multiple repeating structures. And so they're turning up the velocity here, I guess probably a straight line velocity, not a tornado, to look at what the local velocities, effectively local velocities would be on taking the roofs off houses. I see that one of the groups this year also doing some stuff on, in a tornado, should you leave your windows open or closed? I guess that's an interesting question. I'm not sure I know the answer to that, but this is one use of dimensional analysis when it comes down to it. What else do you have going? Yeah, there's a website for it. Other kinds of things, environmental systems engineers will do a class on air pollution, and so diffusion and dispersion in the atmosphere is something that's important, and it gets you can have lots of interesting models, very simple analytical models to look at what the concentrations you'd see would be downstream. And you know that you'd want the flow patterns to be representative of what they'd happen in nature for the particular winds that would be blowing that day. If you have regular winds, you want the flow regime to be indicative of that. And you might also want to know what the influence of structures on the ground in moderating those flow patterns might be as well. So that's that. I guess I want to stop these things from going. What else? Yeah, another one of this. This is the corollary of this is Tacoma Narrows, which you would know about from high school type stuff. I guess the volumes on this. I think this is a lab in Korea, a civil engineering lab, looking at suspension bridges, just like Tacoma Narrows. If you design it wrongly, with the wrong flexibility, elasticity. Aeroelasticity is how structures like wings on planes and bridges behave in flow currents. And Tacoma Narrows, the whole problem is if you look at the section of the bridge, the cross section of the deck, which is usually a deck tapered at the bottom, is if you have flow across that deck, and you see these little streamers showing that flow on the other side, is that as you get higher velocity flows, you shed a vortex from the top of the deck and then the underside of the bridge, and together it's like plucking a guitar string. And so that's what gives the bridge its motion. It's really just like a musical instrument. It has a natural elastic frequency, dynamic frequency, just like your dynamics courses. And if you excite it at that exact frequency, then the amplitude of the oscillation will build. And so you can scale all those things in the lab to be able to do them. You can also use sophisticated numerical models to do that as well. But those are two ways that you can do this. I presume those blocks on the bottom are to give some boundary layer, which is a turbulent layer that's then imparted on the bridge. Two different structural designs here. I don't know what the little dots are on the ropes, whether those are sensors or whether that's just mass to represent the correct mass of the cables. Because it's a function of the springiness of the bridge, the elasticity, but also the mass of the bridge that you want to match. And you can use dimensional analysis to be able to match those, just like you would have seen for Buckingham Pi. And we'll talk about that to close that out today. So kind of a curious area in which to work. And of course, the same reason that you always hear that soldiers should break step when crossing a bridge. You don't march across a bridge lockstep because it sets up a frequency that allows these things to vibrate and maybe tear themselves apart in the case of Tacoma Narrows, right? That. And the final one here is the so-called Millennium Bridge. It goes across the Thames in London to Waterloo Station. And it was built around the year 2000. I guess they're getting ready for the Olympics in 2012. Well, perhaps they weren't, too late, 12 years later. But it's a walking bridge across the Thames from one side to the other, obviously, and it'll come up with something in a little while. And it's not a wind loading in this particular case. It's just a straight bridge, no suspension, cantilevered with a long span so that shipping isn't disturbed. The Thames in London is still tidal, so it's a shipping channel. And you see here the motion of this. This is not a wind motion, but it's a motion of having a lot of people walking across it. And I guess they're talking in the text of this, there's a feedback. So the feedback is you walk across it, it starts to sway, and because it sways, you tend to start walking in step with that period if it's a comfortable period to walk in, and the people around you start walking at that same frequency as well. And as a result of that, it builds. So you see it's just not a wind loading in this particular case, but exactly the same feature is it's got some kind of input into it, which is resonant with the frequency of the bridge, and you can see people holding onto the handrail there because they can't stand up. And so the solution to that is to change the not the aerodynamics, but the elasticity of the bridge. You can either make it stiffer, just like tuning a guitar string, using a heavier string, or using a tighter string, or using a string that has a weight on it. You can do all of those things to change the resonant frequency of this so it doesn't do that. And they did that successfully. And so when you drive around the country here and you see sometimes power lines with weights on them, just utility lines with long spans, those weights are to damp out, change the natural frequency of the system. So that's a bit of engineer mechanics, I guess. I was just looking at that. I thought it was interesting. It's not really fluid mechanicsy. This is definitely fluid mechanicsy, and what we'll talk about today also. And this is just flow in a pipe, and with a dye tracer in the middle of it. So kind of like a wind tunnel, but with liquid running in it. And it's to understand the behavior of the drag in the pipe. So we've talked about Bernoulli, which is inviscid, so there's no frictional losses, but the real essence of what you want to do in engineering design is design pumps to pump fluids against frictional losses, turbine blades to pick up the energy from the wind that's around them. And so that's a transfer of momentum that we're interested in understanding. And so this is, from this behavior that the velocity upstream and downstream must be the same. So this must be a velocity big enough to get turbulent flow. It's no longer a straight shot. Upstream it was straight, and so it takes a while for it to get this turbulent flow as you go downstream. But it must be turbulent all the way, but it just hasn't fully developed until you get further away from the injection point of this dye. So this is just a manifestation. These ripples are a manifestation of vortices which are present in this, and those vortices are representative of turbulent flow. And sometimes you don't want turbulent flow if you're going along, and often you want it. We talked about the golf ball with dimples on it. The dimples are to make the boundary layer break up as turbulent flow, and so there's less drag, surprisingly enough, if you have turbulent flow. And so the golf ball, for a given impulse of force that you apply, will go further. And so that's the whole reason for doing that. And so that's kind of what we'll deal with today. So that's that. So great. That's our eye candy. So I said I thought today we'd kind of recap where we are and talk a little bit about flow and pipes. I guess I sent out an email on midnight. Well, I was actually up at 12:30 this morning, but I didn't send it out. Did it come at midnight? Yeah. But so the scores are there. Look pretty good. I think I didn't usually, when they're bad, you hear back from people, and I didn't get much feedback. I did get some feedback about one of the questions on the key being wrong from a few of you, and so based on that, we decided I didn't catch it. Matt, who checked it after I checked it, didn't catch it. It was half is the crest, not the full length, for the jet, the parabolic jet. So that one was out of 15 points extra. So that's good. So I figured that most of the people who were in this class might have realized that we'd do that, and so it might benefit you. So I'm playing to my audience, my crew. So the scores were the 80, they were 101. So if you take 15 off 101, they're still 86. And I don't remember what the last one was. Do they remember what was 89? 86, yeah. So getting there. I thought it was it wasn't a gut of a test. It was a solid test that was showing you, allowing to show off what you're doing. So I think that's good. So we have two more left. One more is left, the same score as this, the one which is just in the week before Thanksgiving, and the week before Thanksgiving, before you go off campus. And the other one is in the week before finals, but it's for only 10% instead of 20% total because of the Penn State's regs on that, which are there to protect you, actually, that you don't get loaded up with huge, you can't have more than 10% of the grade of a class in the last week of class. So I think that's to protect you, and I think it's a good idea. So any comments on the class? Yep.
Is the final going to be the same format?
Yes. Well, it's not, kind of a final. It's not a comprehensive final. It'll be the last two classes. So the next midterm will be on energy equation, week 8, dimensional analysis, week 9, flow in pipes, 10, and maybe 11, as you see, usually excluding 11:3, which is pipe networks rather than single pipes. And There's always a dimensional analysis question, and there is. And this year there's an energy, there's one from each of weeks 8, 9, and 10. So, but this time, because I'm working on it now. So that's some cheery news. You just got through one. Now he's talking about another one. Good God. So that's the plan. And the final is I guess that was the segue for the final. Final is weeks 12 and 13. So it's a 15-week semester. It's really 13 weeks of classes. 12 is external flows, wind turbines, flows around bodies, and 13 is open channel flows. So really this stuff is the practicality of this class, I would say. The weeks 10, 11, 12, and 13, they're how you design things if you want to be, for all the kinds of things, the disciplines that you're involved in. So I thought we'd spend some time on flow in pipes today, but use it first to recap. Any other comments from what's going on? We have a good-sized class. I'm pleased. So we'll talk about pipe flow today, ultimately. Pipe flow means a section that's filled. I just pulled up this figure just to make the case that pipe flow could be in a pipe, but if it doesn't fill the full section, it's not pipe flow. It's open channel flow. So as you could figure out. And so rather than do that, I'm going to go and use some stuff from before so we can recap basically. Oh, I don't want to do that, actually. So we can recap where we are with the course. And so I'll go through this relatively leisurely, I think, because I think it's worthwhile gathering our thoughts. I think you got a good handle on stuff, judging from how well you did last week. So I'm super pleased with that. By the way, if you're thinking about your grade, there's also a rubric on the course webpage that is an Excel sheet that allows you to put in your actual scores. Always, after finals are done, I always get these questions, well, you gave me a this, but I got this. But there are two settings in Canvas. You can click a link, and it gives you two different scores for where you are. And that link, in one mode, it gives you, for instance, if you haven't submitted one of the homeworks, then it takes it as not being done yet, but still submittable. But of course, if it isn't submittable, it doesn't change the denominator properly in the calculation. So if you click that button, it's the lower of the grades that you get for it. And so if you're not sure how Canvas works or whether it's giving you the right answer, you can put your scores into this rubric. Which, well, sure, I'll bring it up. Do I not? Whoops, didn't need to do that. It's on this. It is, what a happy guy. This. Guess it doesn't open it, but it looks like this. Oops. Is it opening? Yeah. All you need to do is fill in your scores right here. So they'd be out, this midterm 2-2 would be out of 125, but you don't need to account for that. Just put in what your score is, and it will automatically calculate what your grade is. So if you're interested to know how to do that, you just need to pull out your scores for these things from Canvas, make projections on what you expect to do, and you can use that. So that's there for your facility if you so wish to use it. Okay. All right. So it's a marathon, not a sprint. We're in week 10. We've covered a lot of ground. These are our week numbers that we've gone through. Initial starts was properties of materials, week 1. Fluid pressures at a point, week 2. Week 3 was forces on structures. So all of that is statics, even if they were accelerating fluids, as they were in the first class of week 4. And then we talked about Bernoulli. Bernoulli is just a manifestation of F equals ma. There are no losses within it, no frictional losses. You remember the 4 requirements. I'm not sure I can, but no vortices, so irrotational flow, incompressible flow, steady state, and inviscid. So those are the 4 requirements. Inviscid means that viscosity is equal to 0. And so that's an important component. And if we do that, then we can write Bernoulli between upstream and downstream. We know what Bernoulli's equation is. I guess this is the inviscid part. Elevation head, pressure head, velocity head. These are both zeros for Bernoulli because there are no losses. And we need to be able to write it upstream and downstream. Since there are no losses, it could be downstream to upstream. It doesn't matter anymore. And we can accommodate that. We want to be able to have 5 known values to be able to solve for 1. If we only have 4 known values and we want to solve for 1, we need to invoke continuity, which is just velocity times the cross-sectional area. So this would be A1, A2, and this would be, I guess, also P1 and P2. This is old hat to you, right? If you've done this so often before. So we know how to use Bernoulli. It is basically a manifestation of F equals ma. Mass times acceleration is the v squared over 2g term, and the forces are just pressure and elevation, potential forces in the system. We can constrain it with conservation of mass. If we do it for a streamline, it's just area times velocity. Bernoulli requires our densities to be non-changing, incompressible fluids, but we do use it for air, so we do use it for some compressible fluids. So these densities drop off either side, and this allows us to solve Bernoulli when we only have 4 knowns, and we can typically link 2 of the velocities to each other. So instead of having 2 unknown velocities, we have just 1 unknown velocity. We can, so we use that for conservation of momentum without losses, which is really what we're doing. When we looked at the more general conservation equations, we looked at 3 different equations. One was for conservation of mass. It was really an extension of this steady state one. This just says if you have a bucket, the mass flow rate in is equal to the mass flow rate out. If they don't balance, then they accumulate. So we need to have a more sophisticated term to do that. And we write this equation in terms of Reynolds transport theorem. We look at the sum of mass rate in equals mass rate out, and we have a special sign convention for that, which you'll all remember. And if there's a mismatch between what goes in and what goes out, then we have to accommodate it as an accumulation. And we either accumulate a mass in a constant volume, so the density is changing, the tire problem, or we accumulate a mass in a changing volume of a container, such as a bucket where the free surface is rising and the density isn't changing, so we just split this term out in terms of differentiation by parts, and we know it has to equal 0. So that's what we've dealt with there. We talked about conservation of momentum when we can be more sophisticated about how we deal with this expression here. It really just gives us Bernoulli, but it allows us to do it for much more sophisticated geometries than just a streamline. So conservation of momentum for us was our vein questions, firing water into a vein. Water goes up, it pushes the vein. If the vein goes at the same velocity as the water, there's no force that's applied. It's just moving with the drop of water that's catching up with it. If we hold it static, then that's the maximum force we have to apply against it to be able to resist it. And so the vein examples, there's one on Friday, kind of a vein or a plate. And so we can define that. So this is just a much more sophisticated way of writing Bernoulli, which allows us, I suppose, to calculate what the forces are in the system. We kind of did it before. We did a jet lev example using Bernoulli, just by using the pressure of the jet on the ground. It wasn't quite the same answer as using this, and so we used that. Still, using conservation momentum, it's still inviscid. There are no losses in these systems. And so to be able to get conservation of true energy in our system, so this was conservation of mass. So mass would be, what did we call it? I guess we called it m, right? This would be conservation of mass. This would be conservation of momentum. So this one would be sum of mv, not volume, but velocity. We remembered that v is a vector, and conservation of energy would be conservation of mv squared, which you recognize as kinetic energy, right? And so this kinetic energy is pulling something across a table. Once you get it somewhere and stop, then you've used up some energy. To get it back to its starting point, you have to provide energy again against friction. And so this is where we allow for the system not being inviscid, but being viscous. So this is viscous. And so viscosity is not zero. And if viscosity is not zero, then we can account for these terms here. These terms are no longer zeros. And so we represent that in, you might remember we had two ways of writing this conservation of energy equation. One was with enthalpy included, so we could do some chemical calculations for hot steam going into a turbine and generating power. But the more usual one that we said we'd use more often would be just Bernoulli written for the case where it was no longer inviscid. And the case where it's no longer inviscid is where we have these head loss terms and pressure pump head terms. And we can just describe those for streamline as being Bernoulli. Regular Bernoulli is this. This would be regular Bernoulli. This would be what we would call our energy grade line. And this would be what we called our hydraulic grade line for viscosity equals 0. But if we allow these other terms to come in, energy put into the system by having something pumping. Oh, that's good. Between upstream and downstream, then you elevate the upstream energy by some amount HP, and in going downstream you use up those losses by friction against the wall, and that's a head loss. And so now you elevate the energy grade line to this, but I'm not sure whether the energy grade line is really there or here. I guess it's down to this point here, and it means that you're using energy as you go downstream along this pipe. And you're using up energy because you've got drag on the walls. So this is the essence. That's not meant to be an M on its side. It's supposed to be an arrow. And these are shear stresses. And of course, you remember from the first time we met that we talked about Newton's law of viscosity as something like this. You remember this. This is the term viscosity. And really it's just dragging against this. So that's fine. So that's where we were until talking about conservation of energy. So we realized that real systems have energy loss, have viscous losses, and we want to be able to count for them. And we could do some fancy analysis to do that, or we could also realize that there's ways of doing experiments in the laboratory, and we can choose to do the minimum number of experiments to explore some of these systems. And we use dimensional analysis, again, oxymoronic. It's really non-dimensional analysis, so it's a misnomer. And we use dimensional similitude between geometric, kinematic, and dynamic similitude. And so it just means that we put a plane in the wind tunnel, and it has to be exact in form in every single dimension. You shrink everything down so that the ratios of the lengths of the model are some fraction of the ratios of the lengths of the real system, the prototype. And so if you do that, then you have geometric similitude, and your model is a faithful reproduction of your real system. So you have a 777, you shrink it down 100-fold, so instead of being 100 meters long, I'm not sure a plane's that long, but it's a meter long, and every other aspect of it is in similar proportion. And then you put it in the wind tunnel, and you want the regime that's flowing around it to be exactly the same as the flow regime that it experiences in real life. And so the flow regimes have to match. And if you take a golf ball or a hailstone or a cylinder which you flow fluids around, you'd find that if you have very slow flow, you get a kind of creeping flow. So the streak lines that you'd get would hug the shape and come off the other side. If you looked at the velocities around that sphere or cylinder as you go out, we have this no-flow boundary condition where the air, water, is stuck to the boundary of this. So the velocity here is 0, but as you go further and further away from it, you'll get closer and closer to the far field velocity, which is the same as the upstream velocity. And so by having this object in the flow field, you intrinsically change the flow regime. And at low velocities, Reynolds numbers less than 1,000, it would look like this, creeping flow. It hugs the system, and as you go progressively out from it, these kind of hug the system, but they get closer and closer to the far field velocity as you go further and further away. If you flow fluids much faster, then the characteristics of the flow system completely change, typically above a Reynolds number of 2,000, as we'll talk about today. And instead of having this smooth flow, it breaks into this turbulent flow, just like the pipe flow that we looked at before with this undulation. And if you think of this as a bridge deck, actually, the circular section bridge deck, this is exactly what's happening that gives the plucking of the deck so you get resonance. You get a vortex shed from the top, and then you get one shed from the bottom, and so that's just like plucking the bridge deck in some kind of frequency. And this frequency is controlled by the velocity of the flow across it and the viscosity of the fluids. And so you want to, if you're trying to get the forces that are applied on this golf ball, if you're trying to measure those in here, you want the flow regime to be reminiscent of the one at the prototype. So the Reynolds number of the model and the prototype have to be the same. Reynolds number we defined as a ratio of inertial to viscous forces. We did it, I think, on the second class we met from Bernoulli's equation. Density, far field flow velocity, a characteristic dimension, a length. It would typically be the diameter of this, or it could be something else, and the viscosity of the fluid. And so that indexes whether the flow looks like this or looks like this. If we think in real life the flow is going to look like this, when we want to run our experiment at this high Reynolds number. So then, if we run our experiment at this high Reynolds number, we can measure the force that's applied on the structure. And so if it's a wall or a tall building, then we have a model and we have a prototype which we want to calculate. This is what we want to calculate. And this is what we can measure in the lab. So we want, again, dynamic similitude means that the Euler number typically for these systems are the same. Euler number is a ratio of pressure force to inertial force. So I guess it's written here. So this is P over gamma term in Bernoulli equation. This is the V squared over 2G term in the Bernoulli equation. It's just the ratio of those two terms. A pressure is also equal to a force times an area. Oops. So you could replace pressure as equal to some force divided by an area, if you wanted to, here, in which case you'd get this. And so if you go to your model and you measure the force that's applied on the model, maybe with the strain gauges measuring the deflection of a structure that has a given stiffness, you know some kind of area in the characteristic dimension, you know the density of your fluid, and you know the velocity you're flowing at, then you can get the Euler number for the model. And you know that the Euler number for the model, which you can get, has to equal the Euler number for the prototype, which you'd like to get. And typically for the prototype, you'd know the velocity you're flowing at because you're at the correct flow regime. You know the density of the fluid. If it's air, they're the same densities in the wind tunnel as in the system. Actually, on campus we have it's not Garfield, it's the Thomas Water Tunnel. And so just near the IST bridge, there's a water tunnel on the west side of Atherton Street, which is part of ARL. which is the Navy lab, which moved from Harvard at the end of the Second World War to Penn State, and they put torpedoes in there to look at torpedoes running in a water tunnel rather than an air tunnel. And so if you look at the prototype, you know the velocity of the fluid that's flowing, you know its density, you know some characteristic dimension of the system, a height or a width or an area, and then you can get the force that's applied in your real system. And that's really all it is. And so the idea is that if you look at plotting the behavior in your system, you do your experiment at the right velocity, at the right Reynolds number, and you measure the force that's applied at that velocity. So you do your experiment at this velocity model, which is the same as the appropriate velocity for your same Reynolds number. You measure the force that's applied due to that, and you calculate the Euler number. And so you can plot one point on this curve. You run your model at twice the velocity, and you measure the force that's applied. You end up with a second point from the force. I guess you'd have this. And if you have a relationship that goes through those, then you can plot that behavior and extrapolate between them and try and draw some parallels between them. But that's basically what we're doing. And so we could do that for pipe flow. So we're talking about pipe flow today, not really buildings. So let's talk about how that kind of works. So the intrinsic thing is we need these three requirements. Geometric similitude, the model looks like the real thing. Kinematic, the flow regime looks like the real thing. And dynamic, the forces on that structure are proportional to the real thing. And so I think if you looked at the videos from week 9, we can apply these in all the things that we have left to do. And don't expect you to understand maybe all of this today, but you should be at least accepting of the stuff that now we're doing, whether looking at pipe flows or open flows or open channel flows. They all actually satisfy these same things. So pipe flow, we can look at pumping water from upstream to downstream. We have to expend some work changing the pressure from the upstream to push the fluid downstream because it's dragging against the walls on this. And so if we wanted to do some experiments in the lab, we could get the relationships for the behavior of pipes only by doing experiments, nothing else. And we could use something like Buckingham Pi to be able to explain what we're trying to do. And it would go something like this. We'd decide on the geometry of our pipe. Our pipe would have a length, it would have a diameter, and it would have a roughness. And so if we wanted to decide on the components which describe our system, then we could think of what those components would be. So for pipe flow, we have a viscosity of a fluid, we have a density of the fluid, we have a roughness of the pipe, we have the length of the pipe section that we're using, we have a diameter of the pipe, we have the average velocity of flow that's going down the pipe, which would be this, and we'd have a pressure drop. And let me change that pressure drop to write it as dP rather than delta P, because when we do this in another example, delta P is the pressure divided by the length, and I don't want it to be that. Buckingham Pi gives us a way to be able to choose the minimum number of variables that describe our system. It takes the number of variables that we have that describe the geometry in the flow. So we have pressure drop, velocity, diameter of the pipe, length of the pipe, roughness of the pipe, density of the fluid, and viscosity of the fluid. So 7 parameters. And of those parameters, mass, length, and time are all represented. And so this has mass per unit volume, per unit length cubed. So mass and length are in this. And time, this is Pascal seconds. So time is certainly included in this, and also velocity is equal to length over time. So we have mass, length, and time included. So we know from Buckingham Pi, if you've looked at, I think, 9.3, that the number of variables that describe the system is going to be 7 minus 3, which is 4. And so we can start grouping these variables. We could use Buckingham Pi, which is a very formal way of doing it, or we could start guessing what they would be. These are units of length, length, and length only. So the units of length on length describes one potential variable. Roughness divided by diameter. This could also be roughness divided by length, I suppose, but not so relevant, right? You think that in closing off the diameter of the pipe, you think that the roughness would have more of an effect there than over the length. So let's not think about this as a potential. So if we have length over diameter as a non-dimensional variable, we have roughness over diameter, then this gives us 2 of 4, right? So we've said we have 4 potential non-dimensional variables. We've just described 2 of them, so we get rid of some of those. So now we have 2 remaining variables. If we use Buckingham Pi, and I'm going to go down here, Buckingham Pi says that of these variables, let me just write it as pressure. We have pressure, we have velocity, we have density, and we have viscosity. And then we have the geometric terms, which are length, diameter, and roughness, which we've kind of used. And we've used these last 3 to give us length over diameter and roughness over diameter. So those are 2 of our variables. Buckingham Pi just says that we need to take our variables to be able to put them together to get the remaining components. And I'm going to say that let's take diameter and velocity and density. And so Buckingham Pi says that we can get non-dimensional parameters. So these would be what we call pi 1 and pi 2, 2 pi groups. This is going to be what we'll call pi 3, and I'm just going to do it by inspection. And so Buckingham Pi tells us that what we should do is we should write a pi group, which is equal to some variable. I'm going to use repeating variables, which are velocity, density, and diameter. So velocity, density, diameter. And what these repeating variables have to do, because I'm going to do pi 4, which is also equal velocity, density, and diameter. These are so-called repeating variables because they turn up in different pi groups. They have to include all of mass, length, and time. So mass per unit volume, length over time. So these groups include all of those. And so from these then, now I have 2 other variables which are left over. And these 2 variables are pressure and viscosity. And so I'm doing with this prior knowledge. You wouldn't necessarily know this. But if I add, for instance, viscosity here and pressure here, then all these pi groups say is that these pi variables have to have units of mass, length, and time, which are to the power individually 0. And so what I can do is I can put here exponents a, b, and c. And I can specifically manipulate these to figure out exactly what I have to do to get it so that these powers of a, b, and c exactly give me units of pi 3, which are units of mass to the power 0, length to the power 0, and time to 0. So I'm not going to do that here because you'll see that if you look at your 9.3 video, how to do that. This is going to give us a variable which is going to look like These terms are included, so I guess in this particular case, A would be to the power 1, rho would be to the power 1, B would be to the power 1, and D would be to the power 1. It would actually come out the reverse, because this has to be to the power 1. So it actually wouldn't be this, it would be the reciprocal of that. It would be same units, but it would be viscosity over V rho D. So in other words, A would be equal to -1, B would be equal to -1, and C would be equal to -1. And this is 1 over Reynolds number. And so if we go back to this was one of the things we needed to have to be able to have similitude between the flow regimes we'd have. So we make sure we do our experiment at the right Reynolds number. So this one has to be the same thing here. It has to be mass, length, and time to the zeros. And this one, if I just go through it, I'll tell you what it is. It's going to be P over rho V squared, which is an Euler number. In other words, dynamic similitude. And so I suppose in this particular case then that A would be equal to -2. B would be equal to -1, and C would be equal to 0. D to the power 0, right? If you apply this. And obviously this is to the power 1, and this is the power 1. And so it turns out that knowing nothing about the system, we've solved no real equations, solved no differential equations to show us how this works. We know that the appropriate variables that describe this behavior would be the geometry of the system, to these first two, and something about the fluid flow behavior of the system that gives us kinematic similitude. The flow regime that we'd have going through the pipe would be this little die, as we saw in the video to start. We'd be in the right fluid flow regime up here. And if we're in the right fluid flow regime, when we apply that fluid flow regime in the model, we end up with the appropriate force that we can scale in the system. And so the appropriate force that we're applying in the system is just the pressure upstream and the pressure downstream, and they'll be different from each other because we're using up energy in the system, which is the viscous drag on the side of this, which is the other part of the system. And so we'll find out that the behavior of the system is given by these variables. So what that allows us to do is you could do now an experiment where you have a tube and you run flow along that experiment and you run it at different Reynolds numbers. So you run it at 1 meter a second, 2 meters a second, 3 meters a second, 4 meters a second with the same fluid in it. And at those 4 different Reynolds numbers, you plot the pressure drop between upstream and downstream that you measure. And so you end up with 4 or 5 different points that give you a curve. And you plot that curve. So Euler number is you're measuring the pressure drop, you're doing it at a particular velocity, and you're doing it at a particular fluid. So you know everything in here except you measure the pressure drop. In the pipe, you apply a velocity along the pipe. You measure the diameter of the pipe, and you know what the fluid characteristics are in terms of density and viscosity. And so you can plot those. So without knowing anything about your system, you can do a minimum number of experiments that give you a curve which characteristically is linear in the laminar regime. And then when you go above a Reynolds number of 2000, then your flow switches from being creeping flow to having vortices in it. And you get a characteristically different flow. And so if you did the experiments at increasingly larger Reynolds numbers when it's turbulent, you get some dots points that go along here. And so that would define a fundamentally different curve. And so by doing the experiment in the right Reynolds number regime, laminar or turbulent, you have kinematic similitude, so you're exactly the right Reynolds number, and you're measuring the right force in your structure. And so we can construct these figures, and we'll use them. And so I've been a bit long-winded today, but as usual perhaps. But we can do the same thing for the other systems we want to look at today. Not today, but in week 12. So we look at wind turbines, for instance. How do you calculate the force that's applied on a blade? Well, you could think of a closed cylinder as also kind of the same as an open tube. So flow past the closed cylinder is that the flow hits the stagnation point at this end, it goes around it, comes out the other side. For this geometry, you'd expect really to have this behavior that we talked about. At low flow rates, it would be creeping flow. It would hug along the side of the container and over the back side of it. And at higher velocities, it would have vortices off the back side of it. Metaphorically speaking, the back side of it. And so we can do the same thing. We choose to characterize it in terms of some geometry, be the same geometry as this. We do the experiment at the right Reynolds number, where we have a characteristic dimension, which is just the diameter of this. And if we're trying to hold this cylinder in a wind tunnel with a force, then we'd measure a force, which would be a pressure applied on a frontal area, which would be the force that's applied on the system. And we could draw some experimental results by doing the experiment and measuring the force at different flow regimes, and we'd get a diagram which looks almost exactly like pipe flow. In the laminar regime, Euler number would be proportional to Reynolds number, and in the turbulent regime, it would be independent of Reynolds number. And it turns out that if we do flow within an open channel, we can do the same thing. It turns out that for all of the cases of relevance, we're almost always turbulent in an open channel. And as a result of that, we're always in the turbulent regime. We do exactly the same experiment, and we'd find out that the behavior we get gives us an Euler number versus a Reynolds number. We're always on this right-hand side of the regime, and we can characterize the flow. So if you haven't looked at it yet, and I saw that lots of people hadn't looked at 9.3 or colon 3, dimensional analysis is just a formalism by which you can describe these non-dimensional groups. Typically, they come out to be some geometric factors, which give us the geometric similitude, and a kinematic and a dynamic factor, which give us the scaling in terms of a Reynolds number and an Euler number, almost always. But for different systems, you can describe this very formally. And so you can apply this also to other systems, not just to fluid mechanics. You can apply it to the aeroelasticity systems for the vibrating bridges that we talked about as well. And so maybe next time we'll talk about how we actually use this. If I go back to this, I guess I need to do this. To use this for our systems, which would be something that looks like, we didn't go through this analysis, but we will use a figure like this, which is exactly what we're looking towards. And so this is results of the so-called Moody chart, which says that in a laminar regime, our friction factor, which controls flow, is a straight line. And as we get larger and larger flows, we get drag, which is defined in terms of this drag factor, which we can characterize. It's a function only of the relative roughness. So these individual curves are a function of relative roughness, epsilon over d. This curve is completely independent of relative roughness. And so the art of figuring out what pipe flows are is figuring out really how to use this chart to be able to calculate what the pressure drop between upstream and downstream is to do that. That's it. So I got a bit more involved in that than I wanted to. So we'll carry on from that next time. Really, it's just a matter of how we want to be able to calculate the head losses in our system, how to size a pump, how to calculate how velocities would be based on losses in our system, and therefore to design flows in pumping water out of the ground, pumping gas out of the ground, piping fluids in ductwork in houses, etc. So we'll go on with that. So great. Congratulations if you're happy with your performance last week. Looks like you probably were. Great seeing you again.